All right, welcome everyone to first lecture of 188 since spring break. Hope you all had a good break. First deadline tonight, homework 7, tonight at midnight. Aside from that, what's going on is the final contest, which is optional, but I strongly encourage you to take a look at it. And one more announcement is that on Thursday, unfortunately, I cannot be here, and Nick Hay, who was at GSI last spring, will give Thursday's lecture. All right, so we were looking at base nets, and it seems pretty muted here. How is this? Better? I think so. All right, so we're looking at base nets, and we've looked at a couple of things, but let's quickly recap what they were. So base nets give us a representation, which consists of a directed acyclic graph. Each node in the graph corresponds to a random variable. Each node has a conditional probability table, which is a table for that variable conditioned on its parents, where the parents are the nodes in the graph that point into that variable. This base net encodes a joint distribution. The way it does that is by this equation over here, which is saying that the full joint over all variables in your base net is the product of all the conditional probability tables that are in your network. The reason we like to represent distributions as base nets rather than as full joint distributions is that when represented as a base net, the size of the representation grows linearly with the number of variables rather than exponentially with the number of variables. As long as your number of parents for any given variable is relatively low, because the size of a conditional probability table is for a binary set of variables, 2 to the k, with k the number of parents. All right, so here was our canonical example, the alarm network. We have a graph. We have conditional probability tables for each node in the graph. And then if we want to compute the probability of all variables jointly instantiated, for example, this one over here, we just grab all the corresponding entries in the conditional probability tables as follows, multiply them together, and that's our joint probability. Okay, so what we've seen so far is a quick recap of base nets in terms of what they represent. What we looked at last lecture and what you're doing a lot for your homework is what conditional independencies are implied by the graph, by just looking at the graph. What we're going to look at today and next lecture is how to do probabilistic inference. Today we're going to look at inference by enumeration, variable elimination. Then we'll see that in the worst case, things will still be expensive, but often they will not be. And then next time you'll look at a way of doing approximate inference. If you are in the case where you have a base net where things are expensive, there are ways to approximate the answer to your probabilistic inference query. That's what you'll look at next time. All right, so inference is about answering some useful query about the joint probability distribution. There are two canonical examples. One of them is computing the posterior probability of some set of query variables conditioned on some evidence having been observed. Another one is to find the most likely explanation. So given some evidence that has been observed, what's the most likely instantiation of some query variables? Today we'll focus on the first one, this one over here. But the second one can be answered in a very similar way. So if you want to see if you fully understood everything we covered today, what you could do is you could go through the slides and you could see if you can rederive everything for the second one where we derived it for the first one. The essence will be that you'll be replacing summations by maxes. And once you do that, pretty much everything will fall in place the same way. But I encourage you to try it yourself. All right, so the first type of inference is the naive type of inference, which we already covered before, which is inference by enumeration. How does that work? Well, we have some query, and the query has some evidence variables, E1 through EK, some query variables Q, the ones for which we want the distribution given the evidence variables, and then there are the hidden variables. The hidden variables are the ones that are not query variables, not evidence variables, but yet still are in our joint distribution. And since they are there, we have to deal with them. We'll have to sum them out effectively to get rid of them. All right, so here's our query. And the way we answer this through inference by enumeration is to say, well, what we do is we look at the full joint distribution, which for a BaseNet we could construct, right, by just multiplying all conditional probability tables together. Right, look at the full joint, select the entries consistent with the evidence. Then you sum out the hidden variables, which will still be in that table. You sum over the hidden variables to get out now entries that just have the query variables and the evidence variables. At that point, you have the joint between query and evidence. It's not what you want because you want conditional, but then all that's left for you is to renormalize, compute the sum of all the entries in your table, that's z, multiplied by 1 over z, and you get your conditional distribution. Any questions about that? Right now would be a good time to ask about this process because we're going to essentially cover this process for the remainder of this lecture, but finding more effective ways to do it. All right, so let's look at it by example. We have a query here, the distribution for the variable b, which is whether there's a burglary or not, given plus j and plus m. So both Mary and John gave you a call. Inference by enumeration says, well, the conditional is proportional to the joint between these variables. As a reminder, what that means over here is that we're going to rescale. Up to a rescaling, there's equality, and the rescaling is determined by the fact that b, in this case, is the only variable. And we'll build a table over b, and then we'll sum all the entries in that table and rescale by the sum of the entries. All right, this quantity is equal to this summation over here. We have a distribution specified as a distribution over 5 variables, so we need to bring in all variables. So now we have a sum where we sum out over the variables that are hidden, that were not in the query, not in the evidence, e and a. So those are summed over. Also, as a reminder for our notation, lowercase is when variables are instantiated. So e and a are instantiated to take on specific values. Then plus j and plus m are also instantiated to take on specific values here. B is still open-ended. Now we can use the definition of the joint distribution as it's specified through the BaseNet. Get this expression over here. And now we have an explicit expression where we're given a BaseNet, and this expression over here is telling us how from the quantities specified in the BaseNet we can compute the answer to our query. And to spell it out completely, you get this 4 terms here that we have to compute and then sum together. Capital B is still a variable. We're computing a table where B is a variable. That means that we effectively will compute this twice. We'll let B equal plus B compute this quantity. We'll let B equal negative B compute the quantity. And that will give us 2 entries in the table. And then we'll sum those together. That gives our renormalization factor. And we get the conditional after renormalizing. So this is inference by enumeration in a BaseNet. What's not great about it is that if you look at what's happening here is that we have this nice compact representation called a BaseNet. And then when we did inference by enumeration, effectively, we build up the full joint. Because that's what's happening here. We build up all entries in the full joint that are consistent with the evidence. If we have, let's say, 100 variables in the BaseNet, 50 of them are evidence variables, means 50 of them are non-evidence variables, then we'll look at 2 to the 50 entries. Because for every combination of non-evidence variables, we will be having a term like this. So it gets very expensive unless almost everything is evidence. But once you have a reasonable number of non-evidence variables, this gets expensive. Exponential in the number of non-evidence variables. All right, so this case over here, this was our car insurance BaseNet. What do we have? We have, in this case, typically the shaded variables are the ones that are observed. So the unshaded ones are the non-evidence variables. We have 3, 6, 9, 12, 13 non-evidence variables, which means doing this computation will require 2 to the 13 terms to be computed of this type over here, where each of these terms is a product of conditional probabilities, one coming from each of the tables. So it's not ideal to do it this way. So the reason it's slow, because we start with these small conditionals denoted by these little pictures over here, and then we join them all together to get this full joint distribution, which is a big, big thing, and then only we do our computation. What we'll do now, as we switch to variable elimination in this lecture, is we'll find a way to interleave joining CPTs together and summing out over hidden variables. If we interleave this in a clever way, there's a way to get to the answer without ever blowing it up in its full joint instantiation. All right, so this idea is variable elimination. Keep in mind, it's not a silver bullet in that inference in base nets is NP hard. There are base nets where no matter what you do, to compute the answer to the query is equivalent to solving a SAT problem, which is known that nobody has an efficient solution for. Okay, but often this will work out pretty well. Okay, so we'll need some new notation, because these things we're generating along the way here and working with, those are called factors, and so let's take a look at what they could look like. It's a whole zoo of them. So first type of factor. Here we have a joint distribution. So entries are just, in this case, pxy, the joint distribution between x and y, sums to 1. Here's an example. We had the joint between, this case, temperature and weather. This is a factor. Happens to be a joint distribution. You can have a selected joint. What that means is that in your factor, one of your variables or more of your variables are instantiated. So here's an example. Temperature is now cold. You only keep those entries in your table. This gives you a new factor over here called a selected joint. Still of the same form factor as before, but less entries. Doesn't sum to 1 anymore. Factors don't have to sum to 1. All right. What's important to keep in mind as we work with factors is that the number of capitalized variables is the number of variables that are not instantiated, that are still varying. And if they're binary, then the number of entries in your factor will be 2 to the number of these capitalized variables. And so as we work in this variable elimination process, the game will be one of trying to keep the number of capitalized variables small in our factors. If we can do that, then along the way, we never have a big blow up in representation, and we can do things efficiently. All right, here's another set of factors. So a single conditional could look like this. Weather given cold. This does sum to 1. You could also have a family of conditionals. So we have multiple conditionals. In this case, we have weather given hot and weather given cold. Both of those are factors. Both of those are fine. We might have factors that look like this. We might have some that look like this. Really, the essence of a factor is just that it somehow is a table where some of the variables can vary, the capitalized ones, and then there's a number associated with each row in that table. All right, so here's another type, the specified family in this case. So we have, in this case, something specific before the conditioning bar, but a variable behind the conditioning bar. So rain is specific here, but then temperature is left unspecified. Doesn't sum to 1. Doesn't have to. Actually sums to the probability of rain in this case. All right. So the bigger picture here is that there's a lot of things that we can encounter in our process of variable elimination. They're all called factors, and they're all generically of this type over here, where in fact some of these capitalized y's and x's might be lowercase if they have been instantiated. So any factor is anything that effectively is a conditional of some variables given some other variables, where some are still variables, some are instantiated. Let's now see how we can use this. So let's look again at inference by enumeration in the traffic domain, a smaller example so we can fit everything on the slide. Okay? This case, we have rain could cause, traffic could cause being late for class. Okay. We have a table for rain, a table for traffic given rain, a table for being late given traffic. Now we have a query. The query is, what is the probability of being late? What does inference by enumeration do? It says, well, inference by enumeration, we grab the full joint, entries consistent with the evidence, and then sum out over the hidden variables. Everything is consistent with the evidence because there's no evidence. So in this case, we have this is equal to a sum over the hidden variables r and t of the full joint. And we can spell this out in the basenet form factor. This is what we get. All right. This is inference by enumeration applied to this particular basenet. So procedurally, what we do is we track some objects called factors, and the initial factors are conditional probability tables, one per node. Here they are. If we had evidence, then we would have selected out whatever is observed. So in this case, we observed late, then that would have been selected out, and only the ones consistent with the evidence are still present. And then the procedure is to join all the factors together and then eliminate all the hidden variables. So let's break this down what this join is doing. A join of two factors is just like a database join. You have two tables, each factor is a table. Then you join them, meaning that you will now have a new table where the columns in a new table will be whatever was a column in any of your original factors will be a column in your new table. And then the way you compute the entries is by multiplying together the consistent entries. So in this case, let's join table over R and T given R. The join will have as columns a column for T, a column for R. Okay? And the way that we then compute the entries in the join is by multiplying together the consistent entries. So for example, the 0.81 is for negative R, negative T, which is this row over here and this one over here. So that's one operation. That's the join. If we think back of what we did to do inference in the rain traffic late network, we had two joins because we wanted to join together all three of them. So that's possible too. You can join more than one factor together. So let's start with the first join, which we already did, after which we have a factor over R and T, which happens to be the joint, but doesn't really matter what it is. And then we still have the original conditional for L given T. We can repeat the join operation. So we'll now have a table over R, T, and L, because those are the three variables that appear in the original factors. Join on T, get a table over R, T, and L, and here's the table where each entry here is computed from the corresponding entries in the original factors. So this entry over here plus R plus T minus L is plus R plus T, and plus T minus L. Multiply 0.7 with 0.08, you get 0.056. Okay, I've labeled the joins here. I've called one of them a join on R, another one a join on T. The reason we call it a join on R is a join on R means that you grab all tables that have R in them. In this case, we're two tables with R. You grab all of them, join them together, that's a join on R. The second step, we said let's join on T, which means we grab all current factors that have T in them, which was two of them, join them together, and now we've done our join on T. It is possible there are more than two factors that have a certain variable in them, right? For example, if you had a bigger basenet, there might be a variable that appears maybe with 5 conditional probability tables. If it's a child and then a parent of 4 other variables, then the join on that variable would join together all 5 of these tables using the exact same procedure. A column for each of the variables that appeared in the original factors, and each entry in that table would be the product of the corresponding entries in the original tables. All right, so we know how to join. How to eliminate. Eliminating is essentially projecting out your distribution, getting rid of the variables that don't matter, the hidden variables. Okay? You might ask yourself, why do they even exist? Why do we even have hidden variables? The reason we have hidden variables is that because we started with a joint distribution that was over more than the variables that appear in our query. You might say, well, why did you even bother building a model that had extra variables? If you knew they're going to ask you about this query variable, this hidden variable, this query variable, this evidence variables, why do you even have the hidden variables? It turns out that often by having more variables, you can have a more compact basenet. By introducing variables that capture the local interactions between the different variables, you can eliminate the need for having a lot of parents for some variables. All right, so projection operation. So let's say if we have a factor over R and T, and in this case, let's say we want to sum out R, so eliminate R. What we do is we now get a new table. In the new table, R is gone, all the other variables are still there, and each entry in that new table is computed by looking at the corresponding entries in the old table and sum them together. So here, for t, plus t has two corresponding entries, here and here. Those are summed together to get that first entry. That's elimination. Elimination shrinks what we have to a smaller table. So it's really what we want as early as possible in the process. Right, you can do this multiple times, right? So you might have a full joint over R, T, and L. You might first sum out over R, which gives you a table that still has both T and L. And the corresponding entries, again, are computed by summing together. So if you look at plus T plus L, those entries are computed by summing together the corresponding entries in the original table. So plus T plus L is over here, and plus T plus L is over here. Summing those together gives you the corresponding entry, summing out over T. Again, same procedure. So those are the only two operations we need to do inference by enumeration. It also will turn out the only operations we need to do variable elimination. Any questions about the join operation or the elimination operation? All right, moving right ahead then. So multiple joins, namely effectively a join on all your hidden variables. You cycle through all your hidden variables and join on them, followed by then eliminating all hidden variables is what you do in inference by enumeration. Okay? We're going to switch this up and now join on a variable, followed by then eliminating that variable. And there's some important intuition here. The intuition here is that if you want to eliminate a variable, which we want to eliminate the hidden variables, you cannot do this until you have joined on that variable. Because until you have joined on that variable, you haven't brought together all the tables that involve that variable. And it's only once you bring all those tables together, join on them, that you have captured the relationships between the other variables that are mediated through your hidden variable. Because that join is showing you how all those variables interact. Once you've captured that in the join, you can eliminate the hidden variable, and now you still have the interactions between the other variables. If you eliminated first, you would have lost all the interactions between the variables that were mediated through your hidden variables. So it's really important to always first join so you don't lose the interactions, then you can eliminate. All right, so let's do a comparison here. Again, the array and traffic late network will answer twice the same query. I'll show it on the slide. What is the probability for being late? Inference by enumeration looks like this. That's the procedure. Effectively what happens is you start with a join on R, which involves these two factors, PR and PT given R. Then you do a join on T, which involves this new factor that you just computed, as well as this original factor. Join those together. After you've joined, you eliminate R, you eliminate T, and that's the answer to your query. There's no need to do it in that order, right? There's this little thing that you've all seen before, that x times y plus z equals xy plus xz. We can use that property to reorganize the computation that's happening here into this form factor over here. What we did there is we said, well, we can move the summation over R further backwards, right? Because this term here doesn't involve R, so the summation over R can be put right here, and this one was brought up front. That's just applying this property over here in this direction. Okay? We would still join on R, which gives us a new factor over here, factor over R and T. At that point, we eliminate R, which will give us a factor over just T. At that point, we join on T, which will join this new factor here with this conditional probability table. After we have the join on T, we can eliminate T, and we have the answer to our original query. Okay. This is just a small example, but it does illustrate the concept that we can choose how we interleave the operations to some extent. Mathematically, what you're able to do is, if you look at the full joint as the product of all factors, You sum over hidden variables. You can pick one of your hidden variables. You can grab all factors that involve that hidden variable. In this case, the first one we picked was r. So you pick your first hidden variable, r. We grabbed all factors that involved r, put them at the very end, then put the summation over r just in front of them, and that would be our first join and eliminate. And you can always do this procedurally. Pick a variable, one of the hidden variables, grab all factors, move them to the end because the product is commutative. You can always change the order of the product. And then move that summation till right in front of that. If you pick a variable that participates with very few other variables, like here, with very few factors, here there's just 2 factors, then you join just those 2 factors. If there's 5 factors, then you join 5 factors. Whatever participates, whatever has r participates gets joined here, and then you sum out r. What we get here from this process, join and then eliminate, is a new factor, which we might denote as f1 over t. That will be a table with an entry for plus t and negative t. Right. At that point, really we're left with sum over, oops. At that point, we are left with this factor, f1 over t. T is a variable, so we might write it like this. And then this one over here. What we'll be computing then is sum over t, e, L given t, f1 of t. I'm making this explicit here because this is going to be the name of the game, is that these intermediate things are called factors, and we will explicitly compute those and then use them for the next step in the variable elimination. All right, so let's apply variable elimination to this particular example here. Let's pick a variable, a hidden variable, right? Our query was for probability of being late. We have 2 hidden variables, r and t. We can pick any one of them as the first one to join on and then eliminate. Let's pick r because that's what we did before. So pick r, join on r, just happened. At that point we can eliminate r because everything that interacts through r is now sitting in this one table that's over here. This case is just t that participates, but in general it could be many variables that interact through r. We have them now all together. We can sum out r, and this p of t would be our equally well denoted by just f1t, the first factor that we generated in this process. We happen to know it's p of t. For the process we're going through, it's not important that we know what it is. We just know that we're computing a factor and that we're going through this summation and multiplication process that will give us the answer we want. Then let's join on t, sum out t, and we get the answer to our original query. All right, so that was variable elimination in action on this particular basenet. Okay, what if there's evidence? Just like with inference by enumeration, when there is evidence, you just look at your tables and you only retain those entries consistent with your evidence. Right? So no evidence, it looked like this initially. With evidence, plus r, let's say, it looks like this. After that, we can still go through the same process. Right? We still join on the hidden variables, sum out over hidden variables, and then at the end, we have the answer to our query. Okay. So let's say we have a selected joint and we end up with something like this at the end of the day. This is what we would end up with if there were evidence. A table that has plus r and l in it. We know from the process we're doing inference by enumeration. This variable elimination process is just a new way of organizing the order of joins and eliminates in inference by enumeration. That's all it is. We know inference by enumeration. When it's done, when all factors have been joined together and all hidden variables have been eliminated, we're left with the joint of the evidence variables and the hidden variables. And we know all we have to do to get the conditional is to find the normalizing factor by summing everything together in this table, divide by it, and we get the answer to our query. So we just normalize, and we have the conditional of L given plus R. this case, that's how that plays out. All right, so that's it. That's variable elimination. So in a nutshell, it's inference by enumeration, where rather than join on every hidden variable first and then eliminate every hidden variable, you join on a hidden variable, eliminate it, join on the next hidden variable, eliminate it, and keep repeating. Okay, so here's the general procedure. You're given a query and a base net, presumably. In this case, there's some query variable Q, could be more than one variable, and then evidence variables E1 through EK. You need to first pick your starting factors, which are all your conditional probability tables, but only keeping those entries consistent with the evidence, E1 through EK. And while there are hidden variables left, you pick a hidden variable, you join on that hidden variable, which means you grab all tables that have that hidden variable participate in it, join those tables together, then you eliminate that hidden variable, which means for that table you just computed, you sum out over the hidden variable, get a new table, the same variables as before, except for the hidden variable. Every entry is the sum of the corresponding entries in the bigger table. Then you repeat. At the end, it is possible that you're left with just one factor, which in that case will be the join between your evidence variables and your query variable, or query variables. If you're left with more than one factor, you know what's going on. It just means there were some factors that have not been multiplied together yet. They still have to be joined. So if you're left with more than one factor, just join them all together. Now you have your join between the evidence variables and your query variables, renormalized to get the answer to your query. Okay, so that's the procedure. Just like in a lot of procedures we've seen before, there are things that are fixed that are not going to change, and there are places where you can be clever. Any suggestion of where you might be able to be clever in variable elimination? So there's one choice point here, just one choice point, which is pick a hidden variable that hasn't been picked yet. So that's your choice point. That's where you can do something clever. If you pick any ordering of hidden variables is valid. Any ordering will give you the answer to the query that you're asking. But some orderings will lead to very big factors being generated along the way, and some orderings might be able to keep the factors generated along the way very small. And so that's where your algorithm can be smart and can say, well, let's find an ordering such that factors generated along the way are as small as possible, because that will keep the computational load low. Okay. Now we've seen this process in detail. Let's take a look at how we'll often look at this at a more abstract level. And the reason we want to look at it this way is because then if we look at it this way without actually doing the computation, just writing down the computation that would happen, then we can in principle do that for different orderings, see what is the computation that would happen, and then pick one of those orderings and go with that ordering, because that's the one that entails the least computation. So here's what variable elimination looks like on this 5-node basenet, the standard alarm network. We're interested in the distribution for burglary or not, given John and Mary might have called. I haven't made it specific. I haven't said plus J, plus M, minus M, but the assumption is that there's some specific instantiation here that's given. We're going to compute the answer to the query for a specific instantiation. What's the distribution for B? Initial factors are these over here. Then we choose a hidden variable, right, to eliminate. In this case, we pick A. Okay, then we grab all factors that have A in it, join them together. Joining them together gives us a new factor, which happens to be this expression over here. But if you wanted to just write it as our first generated factor, F1, which has J, M, A, B, and E, that's fine. If you want to keep track of what's in there, here's the way it plays out. Anything that ever appeared in front of the conditioning sign will be in front. Everything that never appeared in front but only appeared in the back will be in the back. That's how you get that one over there. J, M, and A were up front at some point, so they're up front. Even if they also appear in the back at times, once up front is enough to be up front. And if you never appeared up front, you just stay in the back. All right, so that's our first factor we computed. Then we sum out. Actually, sometimes we call this F1 prime, because it's before we sum out. Then we sum out, we get our first factor F1, which is only over J, M, B, and E. How many rows in that table? Factor F1, how many rows? 4, right? There is 2 variables, B and E, each of them binary, so 4 possible combinations, 4 rows in that table. Right? So we're now left with these 3 factors. The ones that we used to join and then eliminate are gone, right? So all the ones that had alarm in it, this one here is gone, this one's gone, this one's gone. These 2 are just carried over, and then this new one is also there. Okay, we still have a hidden variable, right? In this case, we still have the hidden variable E, only one left, take that one, join on E. So all factors that have E in it are joined together, then we sum over E, we're left with this factor F2 over here, over J, M, and B. J and M are instantiated, they're evidence. B is a variable, so this factor has 2 rows. One for plus B, one for negative B. What are we left with? At this point, we have 2 factors left. First one that was never used, and then the second one comes from our recent computation. But these 2 have been eliminated. All right, now we just have to join those 2 factors together, which gives us the joint over the evidence variables and the query variables. Then we condition by normalizing, and here we go, we have the answer to our query. Now that we've done this, let's take a look on the amount of computation that's happening in this process, right? So generating this first factor, what do we need to do? Hold on, first one, let's go back. First factor, we joined 3 factors together to compute this table over here. How many rows in that table? There are 3 variables, they're all binary, so this table has 2 to the 3 rows. For each of these rows, we have to do a multiplication of 3 numbers. So sometimes the amount of work is 2 to the 3 times 3, because we do actually 2 multiplications, because there's 3 factors, so it's, but the order magnitude that to us will matter is how many rows in the table, so there's 2 to the 3 computations we have to deal with here. Then we sum out, which touches every one of those rows in that table. So again, it's 2 to the 3 to do the summation. So touch each of those rows. And then the table we're left with is 2 to the 2 rows, large. Okay, so this is one. Then the second elimination here, we have a table generated with 2 to the 2 rows. And we end up then with a table with just 2 rows. So we have 2 to the 3 and 2 to the 2. And then the last one here, that join just generates a table with 2 to the 1 rows. So that's how we summarize the amount of work done in variable elimination. The size of the table is generated along the way. Typically, it'll be dominated by the largest table you generate along the way. So in this case, it wasn't too bad. 2 to the 3 is 8. That's possible to handle. But if you have a very large BaseNet, you need to be careful about the ordering to make sure you keep it low. All right, so let's do this in equations now. So we've seen variable elimination from different viewpoints. We've seen it from the kind of tabular viewpoint. We've seen it from just what are the factors that are being computed with viewpoint. Let's go back to the original viewpoint, where we'll look at it as a summation over a set of hidden variables where we moved around that summation sign and essentially applied this thing over here a couple of times. Okay, so first thing was to say that this conditional is proportional to the joint between B and J and M instantiated. Then we say, well, we don't have access to a distribution over those 3 variables. We only have access to a joint over all variables in the BaseNet. So we'll write it as a sum over the hidden variables of the full joint. Done over here. Then we say, well, the BaseNet gives us a factorized expression for this joint, which looks like this. Inference by enumeration, we then just work on this expression over here. Join everything together, then sum out. Variable elimination doesn't work with this ordering of join and elimination. It actually interleaves things. So we look at the first variable we want to eliminate, A, move all factors that contain A to the back, right? Because in this expression over here, we can put these factors in any ordering. Any ordering is fine. All the ones with A are made sure to be in the back. Then we can move that summation over A till right in front of those three factors. We then actually do our join, sum over A, and get this expression over here. Next variable we want to eliminate is E. We make sure all factors that contain E are in the back, move the summation over E right in front of those factors, then execute the join, the summation, and we end up with this over here. All right, so that's how it works. That's the justification. Question here. Yeah, so a great question is, how do you decide which variables to pick first? And a suggestion here was, pick a variable with very few connections, right? Because per connection you have, a connection means that you're participating in a factor, right? It's a little complicated in that you could be either a parent in the connection, you could be a child, so you might want to account for that. Really what we have here is a search problem, right? You can think of this as you go through your variable elimination process, you can see what are the sizes of factors generated. We had 2 to the 3, 2 to the 2, 2 to the 1. You say sum those together. 2 to the 3 plus 2 to the 2 plus 2 to the 1. That's the total cost of that ordering. You could run a search where your search problem searches over all possible orderings. Cost of picking a hidden variable and joining and eliminating is the size of the table it generates along the way. And then you want to find a sequence that minimizes some of the costs. You could run an A* search, you could run a uniform cost search, it'll give you the optimal ordering of the variables. For this lecture, we're not going to get into the details of how you do the search. You can actually check a past exam to find out more about that. We like to ask you about extensions of what we covered on exams, as you know, I'm sure. So you can read about that in a past exam, but make sure you understand that this really boils down to a search. Often you can eyeball what the right thing is to do. And we also want you to have some intuition about it. When you look at a graph, understand what might be the first one you want to pick. And we'll look at that in this lecture. This one would be better to pick E before A? Yes, it would. Absolutely. And if you do that, you'll see the tables generated along the way will be smaller than what you had in this particular case. Okay, let's look at another example in a kind of abstract sense that will give us some intuition about factors generated, and then we might be able to pick good orderings. So here's our base net. We have a variable z at the top, 3 children, x1, x2, x3, and then each of them has one child, y1, y2, y3 respectively. The y variables are observed, and the query is, what's the distribution for x3 given each of the y variables having been observed? Okay, let's step through this process. So start by inserting evidence in all of the initial factors, which gives us these factors over here as the starting point. Then we pick a variable to eliminate. We can choose x1, x2, or z. On this slide here, I chose x1. Okay? But you could have chosen x2 or z. All of them are valid choices. Some of them might be more efficient than others, but all are valid. Let's pick x1. We grab all the factors that contain x1, which is 2 of them. We join those 2 factors. We sum out over x1. We get a new factor, f1 over x1, which we just generated by eliminating x1. The factors over x1 are gone. All the other ones are carried forward. This is our new set of factors. 2 hidden variables left, x2 and z. Let's pick x2 next. We grab the factors that have x2 in them, join them together, sum over x2, get a new factor, f2, over x2, and x2 is gone, over z and y2, and we retain the other factors. This is what we have now. Then we eliminate z. Grab all factors that contain z, join them together, sum over z. We're left with this over here. All right. At that point, we join those 2 factors together. We renormalize, get the answer to our query. It's important to keep your perspective here, right? When this set of equations is shown over here, keep in mind that effectively what's happening is something as you saw on this slide. Really, we start with an expression that looks like this. Whenever we pick a variable, we're grabbing all factors that contain that variable, sort them to be at the very end, put the summation right in front of it, and then compute that factor that corresponds to the join of those factors and summing out the hidden variable. Right? So this way of looking at it is equivalent to this way of looking at it. It's just different ways of writing effectively the same computation. On this slide, it's made more explicit what the computer would be doing. Computer is computing these factors. Whereas on this slide over here, it's made more explicit how the math works out, why you're allowed to do this, why this is still doing the right thing. Okay, so let's do a little quiz here. We have a base net similar to the one on the previous slide, z at the top. Then x1 through xn are the children of z. Each of them has their own child, y1 through yn. Okay, we're interested in the query shown over here. What's the distribution for xn given y1 through yn? Right? And we are looking at two orderings here. So one ordering is z followed by the x1 through xn minus 1. The other ordering is this one over here. There's many more orderings, right? There's n factorial orderings. But those in some sense are the two most extreme orderings, right? The x variables are effectively all in the same position in that graph. The z variable is the special one. So the decision you're making really is, do we do z first, or do we do all the xi variables first? Let's give you a minute to think about what the sizes of the factors are generated along the way for each of these orderings and which one is computationally better than the other one. And yeah, chat with your neighbor to make sure you come to a good answer. All right, who thinks z first is the way to go? Who thinks z last is the way to go? Okay, most people. All the way in the back with the yellow hoodie. Why z last? Because z has many children, right? And so likely that means it participates in a lot of factors. So let's see how large the factors are that are being generated if z does go first, right? If z goes first, we have ez, we have x1 given z, x2 given z, and so forth till x n given z. We would multiply those together to be a join over those, which would generate a table, in this case, over n plus 1 variables. Which means if they're binary, 2 to the n plus 1 entries in that table, which is pretty bad. So our first step would right away generate a huge table. Then we'd sum out z, bring it down to 2 to the n, but still a pretty large table to deal with. And it doesn't even matter what we have after summing out. What we have before summing out is something we have to deal with. It's 2 to the n plus 1. All right, so what if we keep z for last, right? Let's say we start with x1. If we look at x1, we have x1 given z. We have y1 given x1. We join those two together. We get a table over two variables, so 2 to the 2 entries. So 2 variables here, 2 to the 2 entries. We sum out over x1. We end up with a factor f1 over x1 and y1, which is fixed, which has 2 entries. Okay, if next we were then to pick x2, we would have x2 given z and y2 given x2. That's 2 variables that participate, x2 and z. So a table of size 2 to the 2. We end up with a factor f2 over x2 and y2. Keep doing this until we get to xn minus 1. We generate all those factors up to fn minus 1, xn minus 1, yn minus 1. At that point, we do have to pick, hold on, are we missing something here? I have a typo. This one, after summing out x1, has z in it. This one, after summing out, has z in it, not x2. This one has z in it. And at the very end, we do have to join on z. We have no choice, right? We're joining on z. Let's see. We have many factors to join together over z, right? There will be essentially, this case, n of them. But each of these factors has only one variable in it, namely z, except for the very last one, which will also have xn. So at the point when we join over z, we are joining together f1 over z and y1, f2 over z and y2, up to fn minus 1 over z and yn minus 1. Then we'd also still have p of xn given z. Joining those together will give us a table with just two variables. Xn and z are the only two variables. So we have 2 to the 2 entries, which is pretty small. So everywhere along this process, the tables we generate only have 2 to the 2 entries. Whereas if we started with z, we right away have to generate a table of size 2 to the n plus 1. So the right ordering here makes a big difference. And the intuition that was cited there about z as a large branching factor is exactly the right intuition, right? Because the branching factor tells you about how many factors you participate in. If you want to be more precise, though, you have to simulate what happens. You have to say, if I were to pick this variable, which factors would be joined together? How large are each of these factors that I would be joining together? And then how large would be the resulting join? Because that's really the quantity you care about. It's not the number of factors you bring together, because over here, at the end, we bring together n factors. It's a lot of factors. But the resulting table still is only 4 rows. What matters is the number of variables that participate in all those factors combined. In this case, at the end was just 2, whereas if we did z at the beginning, the factors we had to join together had a wide range of variables, a total of n plus 1 variables, and that's what made it very large. So keep in mind, it's not just number of factors, but really the size of the factor you generate. All right, let's take a short break here. All right, let's restart. First thing, last question that came up during the break here is, why is this one different? Why is there a factor for xn given z, but not for the other ones? And why is there no z comma yn factor? The reason is that xn plays a special role here. Xn is the query variable. And as the query variable, it doesn't go through the elimination process the same way as the hidden variables. Query variables you need to retain. You're not allowed to eliminate them. So eliminating x1 resulted in this factor over here, x2 resulted in this factor over here, and so forth till xn minus 1. But then xn we don't eliminate. When we eliminated x1, what we got rid of was the factor x1 given z and the factor y1 given x1. These got joined together, summed out over x1 to give this one over here. So these are gone now, but xn given z is not gone because we never joined and eliminated on xn because it's a query variable. So that's why it's different from the others. All right, so the difference here is very drastic. It was a specifically chosen example where we have a difference from 2 to the n plus 1 as our largest factor versus 2 to the 2 as our largest factor, depending on which ordering we work with. That's an exponential difference, right? This could be arbitrarily bad. As you grow n, the one ordering is terrible and is pretty much as bad as inference by enumeration. The other ordering is very efficient and requires very little computation compared to inference by enumeration. Okay, so let's look at the computational and space complexity of variable elimination. Okay? Really, what determines the space complexity and computational complexity is the size of the largest factor you generate along the way. That's the key thing. In some sense, it's the sum of the sizes of the factors, but pretty much always will be dominated by the largest one you generate along the way. Okay? So we also have seen now that the ordering that we choose can greatly affect the size of that largest factor. So we need to be careful what the ordering is that we pick. 2 to the n versus 2 is the difference that we encountered. So you might ask yourself the question, is it the case that if you give me a base net and you give me a query, that if I pick a clever ordering, I can always keep the size of the factors generated along the way down pretty low. Right? If there's a way to always find that ordering, then variable elimination can be executed with that ordering and be pretty cheap, assuming you can also come up with that ordering effectively. The unfortunate answer here is no. There are base nets, and we'll see one in one of the next slides, where no matter which ordering you pick, it's going to generate large factors along the way. That's unfortunate. Let's take a look at it here. What does that kind of base net look like? What I'm encoding here is effectively a 3-SAT problem. 3-SAT is a special kind of constraint satisfaction problem where you want to satisfy a clause shown over here. What is this clause saying? It's saying, in this case, there are 7 variables, x1 through x7. I want to find an assignment to these 7 variables such that this clause is true. And this clause is saying x1 or x2 or not x3 has to be true. And not x1 or x3 or not x4 has to be true. And x2 or not x2 or x4 has to be true. And not x3 or not x4 or not x5 has to be true, and so forth. So that's what the top line encodes. That's a 3-SAT problem, an example of a 3-SAT problem. In general, any problem where you have these clauses with 3 variables that could be, that's an or clause between the 3 variables, it could be negated, and then an end of all these clauses, that's a 3-SAT problem, and that's a whole family of problems. As the number of variables grows, the amount of computation needed to find out whether there is a solution or not for the best algorithms that exist is exponential in the number of variables. So pretty bad. It takes a long time to find out whether there's a solution or not. You have to solve a CSP. It's possible somebody at some point comes up with a more efficient way, but it's, for now, nobody has an efficient way of solving this kind of problem. The worst case is exponential. So what I'm going to do on this slide, I'm going to show to you that if you can run efficient probabilistic inference in a particular base net that you can compute from a 3-SAT problem, then if you do efficient inference in the base net and you answer your query in the base net, you also get the answer to your original 3-SAT problem. Which means that if you do efficient inference in that base net, you efficiently answer your 3-SAT problem question. So what that means is if somehow we can efficiently do efficient inference in a base net, then we can solve 3-SAT problems efficiently, which in turn means we did something that nobody else has ever done before. And that's not true. We don't know how to do that. That's exactly what this slide is going to show. I'm going to show that doing efficient inference in a base net, if you can do that, then that implies you can efficiently solve 3-SAT problems, which in turn implies that it's very unlikely that we can do efficient inference in base nets. All right? So what's the base net that corresponds to this 3-SAT problem over here? Well, the first row here, the first row is the original variables. The next row corresponds to a new set of variables that are each of the clauses. So y1 corresponds to x1 or x2 or not x3. y2 corresponds to not x1 or x3 or not x4, and so forth. So that's a very special type of conditional probability table. It's a deterministic conditional probability table, but you're allowed to have deterministic probabilities, right? It's just a special case. All right. So now we have all the clauses encoded. Now really what we want to do is do a big AND of all those y variables. And that will be our z variables, our one z variable. But the thing is, if we do a big AND and we have all the y variables as a parent of this z variable, the consequence is that our z variable has many, many parents. What that means is that we end up with a base net that's not a very compact base net, because a base net where a variable has many parents is a large base net. What we want to do is we want to go from this clause, which is very efficiently specified, to a base net that's also very compact. So we have this staggered way of taking the end of all these y variables here, so we kind of bring it all together, all the ends, in a way that gives us a base net where every variable has at most 3 parents, so it's a very small base net. And this will always be true, no matter how many variables you have and so forth, you can build this basenet with at most 3 parents per variable, so a small basenet this way. So y78, for example, is the end of y7 and y8. Then this one here is the end of y56 and y78 over here. All right, so we've encoded the basenet, a very special one. It's deterministic. Well, the y variables are deterministic, the z variables are deterministic functions of their parents, and the x variables we'll let be random. 50% chance true, 50% chance false. Okay? So what that means now is that if this 3-SAT problem has a satisfactory assignment, an assignment that makes all these clauses true, then this variable z over here has a non-zero probability of being true, right? Because if there's one assignment that makes it through, just one, and the probability for z being true is 1 over 2 to the 7. If there's more than one assignment, then this will be the probability of z equal true is number of satisfying assignments over 2 to the 7. If we were to run probabilistic inference for the query PZ, we find the answer to that query. That answer tells us how many satisfying assignments there are. Which means that it's very unlikely that this can be done efficiently because nobody has ever solved these 3-SAT problems efficiently. This slide is showing you that the worst case is still pretty grim. Inference in basenets with variable elimination. Likely there will be large factors generated along the way. And indeed, if you do variable elimination on this basenet over here, you'll see you'll get pretty large factors along the way. It even shows you that it's maybe even worse than you might have hoped for. It's not only difficult to do exact inference, this also suggests that being able to say whether the probability of a variable being true or false is 0 or not 0 is already a very expensive computation. Because if you know whether the probability for z is 0 or not, you already know how to answer your query. The query whether there's a satisfying assignment or not. All right, so we've seen variable elimination is typically more efficient than inference by enumeration, but the ordering matters, and in some cases, even for a good ordering, even the best ordering will be resulting in pretty large factors, and you'll still have an expensive computation. All right, so we covered this. Now, just like we had for CSPs, we can now start thinking about, are there special graph structures of basenets, past it was graph structures for CSPs, where inference can be done efficiently. One example is polytrees. A polytree is a basenet where there are no cycles, not even undirected cycles. So a directed acyclic graph can have cycles that are undirected, but if you don't allow those undirected cycles, you have a polytree. You can work out on your own as an exercise to test your understanding of variable elimination that indeed for a polytree, no matter what the inference query is, there's always a good elimination ordering that only generates small factors along the way. One thing to keep in mind here, of course, when I say small factors along the way, be realistic, right? If your query is, what is the joint distribution over all variables, then you are going to generate a factor that entails all variables, right? So everything that's a query variable, that's going to appear in your final answer. You can't get around that. You will have a factor that has that many variables in it. If you have variables with many, many parents, those are conditional probability tables you start out with that are large. Again, you cannot get around that. What the ordering can help you with is not growing any of these representations too big along the way. Okay, so try that for yourself to test your understanding. So where are we at with basenets now? We've seen representation, we've seen conditional independence, we've seen most of probabilistic inference, we've looked at inference by enumeration, which is exact, can be pretty expensive because we build a full joint effectively at first. We've looked at variable elimination, which interleaves joining and eliminating. If you have a good ordering, then this can be very efficient. Might depend on the type of basenet you get. If they give you a 3-SAT basenet, that might not be a good ordering. You might still generate large factors along the way. Keep in mind though, often when there is a good ordering, there's also bad orderings. Make sure you pick the right ordering. Pick an ordering that's efficient, not the bad one. Now, given things are NP complete, to do inference in base nets, there is a desire here to do approximate inference. That is, compute the answer to a query approximately, where with a little bit of computation time, you get an approximation. If you have more cycles available, you might get a better approximation, and the more cycles you get, the closer you get to the right answer. Right? We've already seen something like that in the past. We've seen particle filtering. That's an example of a sampling procedure. What you'll see in next lecture, and in fact, the lecture for next lecture is right here. Maybe, Nick, you can stand up for a second. So this is Nick Hay. He'll give next lecture on sampling. You'll see how you can do sampling in general base nets, not just HMMs, where we already saw how to do particle filtering, and approximately compute answers to probabilistic inference queries. All right, that's it for today. Thanks.